We are live. Hey, good morning, everyone, and welcome to Chaos Carnival. I'm Mohan. I'll be your host. First off, thank you for making it here. Um, First things first, let's go through some logistics. If you're watching this on YouTube, you might want to join the live session using the link in the description. We have interactive sessions, we have live speakers, we have booths, and we have boot camps set up on the platform. If you're on our meet, on the left you have the buttons and buttons to access the different sections of the event. We have we have sessions, the launch, and everything on the left side. Or on the right side, you can see the chat box. We have one chat box for session-specific chats, and we have one for the entire event. So make sure if you are typing something specific to the session, make sure it goes into the right box. We have individual hosts in every session who will help you with reading out your questions and also help you with other things. The lobby has tables where you can meet your fellow attendees. You can find the code of conduct at chaoscarnival.io/COC. And if you find someone behaving inappropriately during the event, please report them to us. We want to give you the feel of a real conference. So we have a lot of fun activities planned and also exciting gifts for the winners. I'm sure you'll enjoy all that. As the world gets more complex, the number of moving parts in a system increases, and people are increasingly turning towards chaos engineering. The overwhelming response that we got for the CFPs and registrations is a testament to that. We have a great speaker lineup today. I want to kick things off by introducing our keynote speaker. He's one of the most well-known faces in the chaos engineering space. He's had a long career working at leading edge of technology. He's the Vice President of Cloud Architecture Strategy at AWS, and he leads the AWS Open Source Community Development Team. Please welcome Adrian Cockcroft.
Thank you. Okay, you can hear me okay? Everything fine? Good. Okay, let's just share my slides. Okay, can you see that okay?
We don't see your
Make sure. I'm just sorry. Oh, it's. Oh, I have to. All right. Okay, there we go. Now it's sharing. Okay?
Yep.
Okay, let's get going then. So I'm going to talk today about failing over without falling over. Sometimes we start chaos engineering from sort of the developer viewpoint of I've got a piece of code or a microservice and I want to make sure I'm chaos testing that. I'm starting at the other end, a bit more of an operations point of view, which is, how do we bring the ideas from disaster recovery into chaos engineering? So first of all, I'll talk a bit about chaos engineering itself and what I mean by failing over without falling over, and then I'll have a little bit on the new AWS contribution in the space, the fault injection simulator. So chaos engineering. I have a sort of a little more concise definition of the term than the one that a lot of people have been using. So the point here is that we're going to have failures. That's a given. We want to mitigate the impact of those failures, but we need to experiment to ensure that the impact of those failures is being mitigated. So this is it's not really any different to sort of QA testing and the things we've been doing in historically, but the point here is that we're doing this in an operational sense because rather than just looking at bugs in the code, we're looking at what availability impacts we could be mitigating. If we look at chaos engineering as a term, put up a Google trend here. About a decade ago, more than a decade ago, we did the first Netflix blog post about Chaos Monkey. And one of the reasons I think that chaos engineering emerged around that time was that we had cloud and we were able to set up our environment so that we could figure out how to automate what we were doing in a way that we had not previously been able to do. If we look at resilience, decades ago, maybe 40, 50 years ago, there was disaster recovery emerged as a concept in backup data centers. And that's been something that people have invested in a lot over the years. Nowadays, most people, I think, are aware of chaos engineering. A few people are doing it regularly, and even fewer people have it as kind of a way of life. I think what we really need to get to is a future where we're continuously testing and proving that our systems are resilient, and chaos engineering is the tool we use for doing that. I've also run into some customers that say, I don't want chaos in production. That's just a visceral reaction. So maybe we talk about, would you like continuous resilience in production? And they say, yes, I definitely want some of that. And we just don't tell them it's the same thing. We're just giving it a different name and running it all the time in production. So sometimes the what you call something matters. So what we're really talking about here is that if we build redundancy into systems so something fails, we can fail over to an alternative. But that ability to fail over itself is complex and hard to test. So very often the entire system falls over. And we've seen many examples of this where a small failure escalates and ends up taking out the whole system. So how can we do better? The first thing, I used to have a diagram showing a chain, and you're trying to find the weakest link in the chain, but that's actually the wrong analogy, because chains don't show you they're going to fail until they suddenly break. If you look at a rope instead, or a cable, it has lots of strands in it, and what you can do is see how frayed is my rope, how many strands are left, and then the fact that the last strand broke at some point, that last strand breaking isn't the cause of the failure. That's the proximate cause, was a strand broke and something fell. But what the real cause is that you let the rope get too frayed. So we should be building our resilient systems where we know how much margin we have and we can see how frayed our ropes are in some sense. So you have to have a way to see how much extra capacity you have in the system that is there to support your resilience. Really key book here is Drift into Failure. I've been talking about this book now for a very long time. And the important point here is that even if everyone does everything correctly at every step along the way, you can still get a catastrophic failure because people are optimizing locally rather than optimizing for the big picture outcome. And if you've never had a certain type of failure, then people start believing it can't happen. And all of those safeties that were built into the system to prevent it happening gradually get consumed up by economic pressures typically. Well, we could optimize this, or we could save some money here. And you keep going until finally you get that big failure that was originally designed out of the system, right? And it's a huge surprise because no one's ever seen this failure before. So that's the kind of failure that we're trying to watch out for. If we look at chaos engineering, I like to divide it as a sort of architectural pattern here. We've got the infrastructure at the lowest level, which is normally cloud-based nowadays, and we can have lots of alternative ways to get something done. The key point with the infrastructure is you have redundancy there. Above that, you have to have a way to switch between those alternatives. This is the part that is usually very poorly tested. This is the thing we're exercising with this type of chaos engineering. We're exercising failures to cause the switches to operate, to show that they operate correctly. Above that, you've got applications, and applications need to work even when there are timeouts and retries and failures and parts of the system are not completely happy. Those applications need to be tested in that way. And then people, because people that have never lived through a failure, they don't know how to coordinate and fix that problem, and they can cause more problems. So we need to work at all four layers in this. And it's not just a chaos engineering team that's exercising this from an availability point of view. It's also a security penetration test, a security red team that's trying to find the security weaknesses. I've heard from some customers that if they look at the causes of downtime in their application, the most significant cause of downtime is no longer hardware failures or configuration failures or software bugs. it's actually related to cybersecurity issues, like denial of service attacks, needing to take something down to patch it for a CVE or something like that, the 0-day kind of security problems. So we're seeing that security is actually causing potentially as much downtime as the traditional causes of low availability, which is hardware and software bugs. So I think we need to treat this holistically. The fault injection simulator from AWS has actually got an extra thing, because it's not just running these experiments to ensure that availability is being handled. It's also got some extra things in it which I think are relatively unusual in the chaos engineering world, which is also looking at the performance impact of failures. Because a failure may not take something down, but it may cause it to perform poorly enough that customers will notice. And we want to be able to make sure we're covering performance impacts as well as availability impacts. Chris Pinkham was the original engineering manager for EC2 a very long time ago. I was doing a panel session with him back in 2010 or so. And he said this, I wrote it down, I've been repeating it ever since. You can't legislate against failure. I mean, you can't design out every possible thing that can go wrong. But what you can do is focus on fast detection and response. And fast detection is what we call observability nowadays, the ability to see what's going on inside your system. But you also need the ability to control and have ways to respond and manage your system. And that involves getting people and the systems and the automation aligned. I think there's a lot of useful work that's been done over a long time in safety critical systems. So let's have a look at another book here. Engineering a Safer World is a book that I really want more people to read. Systems thinking applied to safety, from almost a decade ago now. They have a series of systems theoretic process analysis and the accident model and processes. They have a bunch of acronyms here. But there's a lot of free content at MIT, at their website. They run a conference every year, and they actually include security as well as availability in their hazard models for safety. This is about thinking about the hazards that will affect the safety of your system. When you do this from a control theory point of view, we draw a control diagram. This is a little different to the way we'd normally draw a software architecture diagram. The way a control diagram is set up, you typically have sensors, which are flows moving upwards in the diagram. Controls are flows moving downwards in the diagram. So at the bottom here, we've got the data plane, which contains a web service in this case. Customer requests are being processed. That's what the business logic is for. That's why we built this thing. But we also built a whole lot of code for managing that data plane, which we call the control plane. There's a control algorithm, which might be, say, an AWS autoscaler, or it might be a fraud detection algorithm that's controlling, rejecting certain customer requests or preventing DOS attacks or something like that. All of those are control plane. And then that works off a model of the control process, which says that if the data plane's getting busy, add some more machines to it, or if you see traffic from a suspicious IP address, block that traffic. Those are the kind of models that are in that automated control plane. Now, control planes can only cope with the things that they were designed to control with. So we have a human operator as another level of control plane who's watching over the system to make sure it's staying in control. In control means the control plane can manage it. Out of control means the control plane can no longer cope with whatever is going on. That's the kind of definition, if you like, of in control and out of control. So if the system's out of control, the human controller has to decide what to do. They have to look at what's going on. Maybe they're looking at throughput to make sure that the system is processing at the rate they expect. And they have a bunch of runbooks and things like that that they use to manage both the control plane and directly actuate on the data plane. So this way of thinking about it, you can see there's basically two feedback loops. There's an automation feedback loop and there's a human feedback loop. And thinking about the way that human feedback loop works is something that I think we really need to focus on. The usability of our systems under stress and in failures is one of the major causes of additional outages and escalating outages. So what happens if there's a big enough disturbance to break the web service? So by this point, what I mean here is that something goes wrong that is enough to cause the system to effectively be out of control. Maybe the automation itself had a bug and broke. Maybe there's some external thing like a network partition, so customers can't reach the application. Or maybe the application crashed and corrupted its data stores, so it's not restartable. And anything else you didn't think of. These are the kind of things that cause you to, you know what, this system's more broken, I can't easily fix it, I'm going to fail over to an alternative system. And this, what I drew previously, I didn't have an alternative system. So let's redraw this in a way that's relatively familiar to the way we roll out applications on AWS using availability zones. So within a region, we'll have 3 availability zones. They're separate data centers, but they're close enough together that you can do synchronous writes. So the data always exists in all 3 zones. And so that means that the data is consistent, updates are consistent, and you should deploy your services so that you have services across all 3 zones. And we do a lot of work to make sure that the failure modes of the zones are independent. They're roughly, let's say, between 10 and 100 kilometers apart. They're in different floodplains. They're connected to different power supply sources. They aren't different pieces of the same building, basically. So the assertion we're making with availability zones is that you should be able to lose a zone and keep working. And there should be no downtime. You should have some retries perhaps, but everything should just keep going. But what you need to do that is a service which is capable of routing traffic across these 3 zones and noticing that one zone has gone away and dealing with it. So in this case, I'm going to assume that we've lost a zone for whatever reason, and we're now running on 2 zones. What we want to happen is the routing service should route the traffic to those 2 zones, and the routing control plane should be the thing that tells the human controllers, by the way, zone C is offline, I'm running on zone A and B, everything's cool, we've scaled up the capacity in these 2 remaining zones, you should probably call someone and find out when zone C is going to come back again. So that's what you'd like to happen. Unfortunately, unless you've tested this really carefully and done it a lot of practicing, this isn't really what's going to happen. So I'm going to run through now a much more realistic scenario for what actually happens. I'm going to look at this in terms of the way that STPA does it. The way STPA looks at this, we look at all the components in the system, and rather than saying, what happens if this box fails? Instead of looking at the boxes in the system, we kind of look at the wires in the system, given this is sort of a box and wire diagram. What we care about is the information flows, and do you have the right information flows to cause the system to stay under control? And so we look at the hazards that could disrupt different types of flows. And first of all, we're going to look at the sensor metrics. These are the flows going upwards, the observability flows. So this is a checklist for observability. What could go wrong? Well, maybe you don't get updates from the system because something went down. Maybe taking that zone offline broke your entire observability system and it's no longer reporting anything. Maybe it started reporting zeros, or maybe the integers overflowed, or you got corrupted data for some reason. Things are being overwritten. Maybe something went offline, or it's coming on offline and online intermittently, which means it's delaying data which is being mixed with newer data. So you start getting things out of order. We've all seen logs scrolling up the screen faster than we can read, so that's too rapid. Or maybe it's just going too slowly. You're getting an update every minute, whereas you can't see what's happening on the second by second level. Maybe you're getting updates every second, but they're delayed by 5 minutes for some reason. And then there's coordination problems where think of systems which need to all be, maybe you've got different versions of the system running at the same time, and that's causing some kind of coordination problem. And also over time, as we roll out new versions of software, sometimes we break things without realizing it. And maybe in this failed mode, there's some sensor metric which is actually broken, but you only found out because you're actually in this mode now. So what's actually likely to happen? I think the control plane isn't going to clearly tell you that everything's taken care of. It's much more likely that there's going to be a huge flood of errors, and whatever dashboards and tooling you have is going to be seriously impacted by all the error handling. So now let's look at the model. So there's three parts to this, right? There's the sensors, the observability, and then there's something, we talk about observability, but there's effectively this thing called modelability. Do you have a model that correctly reflects the ability to take a sensor and turn it into an action? Something like, if the CPU gets busy, add more capacity, right? That model is the thing that says CPU busy means you need more capacity. That's the rule, is part of the model. But that model may not include looking at memory. Maybe you're out of memory and you need more capacity. But the system, if you run out of memory, quite often systems actually don't run out of CPU because they're busy trying to get memory. So your system starts looking idle, and maybe your control plane starts scaling the system down when you get out of memory, when it should be scaling it up. All kinds of things can go wrong if your model is looking at the wrong metrics. The memory metric may be there, but your model may not be looking at it, for example. So that's model mismatch. Maybe there's a mismatch between the model that the automation has and what the human controllers have as well. Again, some of these are very similar hazards, but some of them are a little different. Maybe you have more than one model. Maybe the human controllers each have a different model in their head because they have different experience and different training, and they look at the same metric and they think they should do different things. So that those metrics mean different things. And also, again, degradation over time. Human controllers forget things, right, in particular. So the humans are going to be confused. There's going to be floods of errors, displays that are lagging, and out-of-date runbooks. So this is kind of the normal situation. Now we look at the controls, and controllability is another thing. So we have observability, modelability, and controllability. These are all things that you need to think about. So how controllable is your system? And maybe you didn't provide a control, or you did something unsafe, or you did it too early or too late, or in the wrong order. You started doing the right thing, but then stopped it before you should have, or kept going too long. Maybe there are conflicts. Different controllers, different humans have different ideas about what to do, and coordination problems. If everyone isn't on the same central call or Slack channel or whatever, then maybe one person makes one change and somebody else makes another change because they aren't coordinating. And over time, we've all seen out-of-date runbooks. So what's actually likely to happen is that the human controllers, although they probably shouldn't need to do anything, they're going to be confused, they're going to try to fix things, and some of the tools they've got are going to be broken. So what's most likely to happen is that the entire system is going to fall over. There's going to be this inrush of extra traffic and a lot of extra work going on because you're going to have a request retry storm as all the different zones try and talk to each other and try to talk to things that are no longer there and no longer working. And this is likely to cause a complete failure of the application. And this is the point where a lot of people in the audience probably have some kind of post-traumatic stress disorder reaction because we've all seen this happen a few times too many. And then also this routing control plane is also going to be impacted. It's a distributed thing. It probably also is running partly in control plane, in zone C. It's got its own problems, and it may actually keel over as well, and your whole system is down, including your ability to see whether it's up or down. So it's obviously a bad situation. I'm just saying that the first time you try this is the most likely outcome. You have to work through and debug and tune your system so that it will fail over correctly. So how do we fail over really without falling over? Two things that are really critical. One is alert correlation. You've got to take floods of alerts and you've got to reduce them to actionable insights. And there's a few tools out there that you can use to do this. There's Big Panda and Moogsoft, and AWS has a new tool called DevOps Guru that looks like it's going to be useful for this kind of thing. But you need some way to take these floods of information and collapse them to, no, really there's just one thing, underlying problem here. And your observability system needs to cope with these floods without failing itself, so you can actually see what's happening. And then you've just got to run regular chaos engineering experiments to prove that the system works in these states. And the fault injection simulator has a little bit of deeper insight into the system. It can actually get into the networks at a level that, and the control planes that AWS has, in a way that you couldn't previously do with third-party tools. So think of fault injection simulator as going deeper into AWS, but not necessarily having the breadth of some of the other tools that are more mature. And then there's retry storm. So we want to prevent work amplification. I've written blog posts on this in the past, but you want to reduce the retries to 0 and have short timeouts. And this is so that you don't end up working on orphaned requests. An orphaned request is one where somebody at the edge of the system has requested something and they've timed out and given up and maybe retried or have gone away. And the system is still desperately retrying to produce a result that the original requester is never going to see because they've given up. So you want to make sure that you use short timeouts and you fail fast to an edge point at the subsystem and retry from there. That will make the system much better. And the other thing is routing calls within the same zone. This is something that's not obvious because a lot of people, you have your microservices and you're just picking another one to talk to and you don't zone scope it. Any microservice in zone A should only be talking to other microservices in zone A. It shouldn't be talking to B and C. The only things that should be talking across zones are data replication services. So your writes, your stateful writes should be written across zone, and that should be the only thing, not every service calling every other service. This is something we developed like a long time ago at Netflix. Some of the other customers I've spoken to have this in their architecture. I know Uber's microservice architecture has this built in. But if you don't think about this, you will discover that you're generating a huge amount of extra failure when you lose a zone. So how do we make this simpler? And you get simplicity by having symmetries and using patterns and making things look the same everywhere. And one of the nice things about cloud is that this really high level of automation, consistent configuration, and the instance types and zones and regions are the same across regions. So one of the problems in data centers is every data center is different and they drift. And you don't really get the same kind of drift in a region, across regions and across zones that you get across regular data centers. So that is an extremely powerful ability of cloud to automate these and start productizing disaster recovery in a way that was never really possible in the data center. So you want to have these principles to try and make things look the same if they are the same, but it also surface differences, but also test those assumptions. If you think things are supposed to be the same, you can have chaos tests that try to test that assumption. So really talking about multi-zone here, what about multi-region? Talk to a lot of customers that are trying to figure out a multi-region strategy. The first thing is get your zone failover solid before attempting multi-region. And one of the maybe not obvious reasons for doing that is if you see a failure, the first thing you have to figure out is this a zone failure or is this a region failure? If you can't cleanly handle a zone failure, you can't disambiguate whether this is a zone or a region failure, because zone failures should be automated, no data loss, just everything should just keep working. A region failure, you've usually got eventual consistency, and that means that when you fail over, you have to be more careful about stopping things, restarting things. It's typically a manual failover when you go cross region, and an automated failover for cross zone. So in that case, you have to decide, do I push this button or not? And that decision needs to be very well informed. And if you're suffering from the problems I was just talking about in your zone failover, you have actually no idea whether you should push that button or not. We can use STPA, the same technique, to look at multi-region specific hazards. It's just the same technique, the same hazard checklist, but you're looking at a different control diagram that's a little more complex. And we have lots of well-architected patterns to guide you. So now I'm just going to give a brief overview of the fault injection simulator. This is based on some slides by Adrian Hornsby. If you want to watch a full version of this with a demo, some demos of the tool, then you can look up EMB 412 on. It's actually now up on YouTube. All of the reInvent talks were posted last week. So this is sort of Adrian Hornsby's version of sort of what is going on in chaos engineering and why is it difficult? Well, we're stitching together tools and homemade scripts. It's difficult to ensure safety, and it's difficult to reproduce real-world events. And what we've built is a fully managed chaos engineering service that is easy to get started and to share experiments. It manages a bunch of real-world conditions, but it's also got a bunch of built-in safeguards. So it's integrated in the management console and the CLI. Use your templates to get started, and then you can customize those templates and share them. You can run experiments in sequence or in parallel. You can target all levels. And we have real faults injected at the service control plane level. This is the bit which was not really possible with other tools. But I think what we'll see is other chaos engineering tools using the fault injection simulator as kind of as a layer or an engine for managing these very specific additional faults. So I think we're going to see tools come together and calling into each other to get these kind of capabilities. So we're exposing certain capabilities through fault injection simulator that are not possible any other way. And there's some safety conditions around that, like that particular AWS account has to be enabled globally and they're off by default. So you can't accidentally run a fault injection in an account that wasn't previously set up to be a target for it. As sort of the common practice, there are stop condition alarms, there's integration with CloudWatch, built-in rollbacks, and then fine-grain access management to make sure that only the people that should be injecting these failures can. This is kind of how it works. You've got your IAM, your management console, using the fault injection simulator. If you start an experiment, it starts modifying, or, starts injecting failures into the resources. You've previously set up some stop conditions, and CloudWatch and EventBridge are looking at those, and those are feeding information into the tool to stop the experiment. Third-party monitoring tools are included here. So if you're using Datadog or whatever to monitor your system, if Datadog sees something bad, those events can be fed into the system to stop it as well. So different components, actions, targets, experiment templates, and experiments. Just quickly look at those. So actions are, okay, there's a service name and an action type, different faults, duration, timing, things like that, rollback behavior. This is defined as a JSON. So this is the actions as a JSON, the typical kind of thing you might expect. And then a target tells you the things that you're going to go after in the selection mode. So here's an example showing the different ways you can specify targets. And then we can have a template that says the overall definition of an experiment. And so it's got a name, a description, a role, stop conditions, and then a bunch of targets and actions like we just looked at. These can be structured in different ways. You'll see lots of examples of ways to do this. And then once you run that experiment, once you run that template, now you've got an experiment. That's the conditions, the actions, the results, what's going on. And these are the initial set of fault injections. See, server error, API throttling, memory and CPU load. There's a mixture here of things which are managed using the systems manager daemon, which we install on instances on AWS instances. So some of these are done using that basically daemon, and others are done at the control plane level. We have some of them also for EC2, ECS, and EKS, and then a few on RDS as well. And this is the area where we expect to do most work, because getting the basic capability is out, and then we need to go through and figure out how to work across the product line, all of the different services that AWS has, and add the correct support fault conditions and injections on it. Okay, so I think as data centers move to cloud, these really fragile and manual disaster recovery processes have been standardized and automated. We're building more and more automation, and we're starting to see well-standardized patterns. So somebody, for example, that learns how to do AWS failover successfully in one organization can move to a different company or a different team and see, okay, we can just implement the same thing. Now, if you look at doing that between data centers, that's not going to work, because data centers are so different. But as long as you're using AWS, that's going to become a transferable skill set. And what this is going to do is it's going to harden the patterns. It's going to have, I think, a much more reliable and automated world, where we're taking what has been traditionally a pretty scary annual experience that's a big pain in the neck to do, to something that's automated and continuous. What I mean by continuous, I think that the right cadence to set this up at is something like every 2 weeks. If you're trying to get into chaos engineering, I recommend that you set up like every 2 weeks a 1 or 2 hour meeting. You get people in a room and you start with paper exercises like, okay, what happens if the site is down now? Can everyone pull up the right dashboards? Do you know how to log in? Where are we coordinating? Nowadays, since we're not meeting in a room together, we're meeting on a video call. What if that video system's down as well? Okay, what's the phone number that we're going to coordinate on? So we'll just practice everybody knowing how to get together and coordinate, and then pull up the right dashboards, make sure the right people have the right credentials to log in, the right credentials to perform the actions, the control actions. There's a lot of basic groundwork of forming the human side of team forming, of how to quickly detect and respond to incidents. That in itself is valuable, and making it every 2 weeks means it's top of mind. And then 2 weeks later you meet and you say, okay, what did we fix since 2 weeks ago? We found a bunch of gaps. We found some broken dashboards. We found something that wasn't well documented. Okay, 2 weeks later we fixed those things. What are we doing next? Eventually you start running example scenarios in a test environment and shutting things down for real. And then eventually, maybe even years later, you finally get to the point where you have applications which are surviving every chaos attack you can throw at them in test, and you start running those applications in a production environment where you are doing chaos attacks on them. So I think this is the idea here being you're doing continuous improvement and continuously making your resilience better. And then you've also creating a stance where you are continuously able to be sure that you can take a failover at any time and cope with it. So here's some resources. There's some talks from reInvent. As I mentioned, these should all be on YouTube now. So there's a Capital One example, a multi-region example from Autodesk, Adrian Hornsby's talk. I think Adrian also did the testing resiliency talk. And my blog posts on failing over without falling over. There's a long write-up of this on Stack Overflow that was quite a detailed blog post. And then some things on response time and retries and timeouts on dev.to. Getting a little outdated now, but this paper I wrote with Pawan Anigotri, he did most of the work. There's a lot of detailed information here on how to structure your networks for building financial critical applications in particular. And then I've got my book list recommendation. Okay, so that's what I had. I just want to give a quick plug to the regular resources that AWS has, the well-architected framework, labs, architecture center, and the solutions library. We'll be augmenting this with a lot more around the failure injection simulator as we roll that product out, that service. So thank you. And welcome to the conference, and hope everybody has a good time, and look forward to seeing all the other talks. So thank you very much.
Thank you, Adrian. So let's take a few questions. So you were talking about how the resilience playbook is a transferable skill across companies, and now that AWS, we cannot do that for data centers, right? And do you plan on making the FIS also available with other cloud providers? That's also the question Sindel has asked in the Q&A.
No, I think it's the point here is that we wanted to be able to do things that you couldn't do from outside with the regular APIs. So the point of FIS is to really be the AWS mechanism for doing fault injection. The parts of it that can work outside AWS are the things that are run through the Systems Manager daemon. Now, the Systems Manager daemon can be installed on any Linux machine, basically. It's available for Intel and ARM architectures, and you can put it. I used to run it on a Raspberry Pi at home, so that I had remote management of a thing I was automating, right? So you can use it for things that are in your data center and on other cloud providers, and so that's one piece. And then the other thing is, if we look at the way that we're starting to do a more distributed cloud, things like EKS Anywhere, we've got the ability to run a Kubernetes control plane on AWS, but the nodes elsewhere. So it's still useful in that sense. You can run the Kubernetes nodes in your data center or another cloud provider, but still have the control plane on AWS. And we also have a distro of EKS, so you can run the AWS version, if you like, of Kubernetes setup elsewhere on the data center, if you like. And again, there are some things that you could potentially connect into that because it's operating at the Kubernetes control plane. So, but I think the Kubernetes aspect of FIS is still emerging. Like, we're really focusing on the AWS networking and EC2 control planes, the things that you can't do any other way. And then we'll look at customer demand for what people want to do with it. And we'll add some interfaces to things like Kubernetes, and which is, as usual, AWS is customer driven. So we'll look at what people ask us to do. But I think this is ultimately, I think that all the cloud providers should have a set of interfaces for doing chaos injection that reach under their APIs and can touch the underlying systems in ways which wouldn't, in a safe way, in a controlled, experiment-driven way. So this isn't something you'd have in a normal API. And I think once that happens, some of the more general tools like, say, Gremlin, which can give you cross-cloud portability, can actually call into FIS and do a specific thing, use it as a particular type of attack or whatever you want, however you want to look at it. So I think we'll see some layering, and more tools are better, and we'll figure out ways to connect all these tools together over time.
So related to that, would FIS be available as part of the AWS Cloud CDK?
I assume so. I'm not sure. I mean, it's got CLI and API, and I'm not sure how you'd. CDK is really to create the resources. I don't see why not, but CDK is an open source tool, and we've got a lot of contributions from outside. So if there's a point at which it makes sense to add it to CDK, someone will add it. I think that's generally the approach I'd see. Like, roughly half the contributions to CDK are from outside AWS now. So it's just, I think CDK, talking about the patterns that we're using, CDK patterns, which is actually, there's a whole CDK patterns website. It's a really powerful way of building those patterns in a very consistent and concise way. And if your daily work looks like what I call death by YAML, like just piles and piles of YAML files, CDK will reduce thousands of lines of YAML to tens of lines of code you can actually read and manipulate. And that's a really useful paradigm, I think, going forward. Just looking at some of these other questions here. Yeah, FAS isn't available yet. It's still in preview. We announced it in December. So the difference between a zone and a region. So the difference is zones are close enough together that they're a few milliseconds apart, meaning that they are tens of kilometers apart. That's the zones, and they're separate data centers. So when you look at data center failover, there's some people do local data center failover like across town, and that's fine until like the entire town gets taken out by something, say a flood or a storm or something. Sometimes you need to be further away, and a region would be, we have different regions in different countries for geographic, for regulatory diversity and things like that, but also particularly in the US, we have multiple regions, like we have Virginia, Ohio, California, and Oregon. Right? Those are separate regions, and you can do failover between those regions. And if you want relatively low latency, maybe you go from Virginia to Oregon. If you want very high availability, you might go all the way to Oregon. A lot of people run between Virginia and Oregon to get the US is divided into three power grids. There's basically East, West, and Texas. And so sometimes there have been cases where the entire power grid for a third of the US has gone out. So some of the financial industry regulators make sure that that financial institutions have locations that are in multiple power grids. So they'll be in, say, New York and Texas, or New York and or Virginia and Oregon, or something like that. And those are regulated, and you can argue with regulators, but fundamentally you follow the rules. And the idea being that these are extremely separate. Now the problem then is they're like 100 milliseconds apart, or if you're failing over between Europe and the US, maybe several hundred milliseconds apart. And you can't do synchronous updates across regions typically without it being too slow. So the point really is that between zones, you do synchronous updates, and you can be consistent across those zones, but across regions, it's eventually consistent, and you need to manage that consistency yourself, kind of at application level.
All right, Adrian. Thank you for the session. So up next, we have a 15-minute fun activity, I guess. The team here has planned some quiz and some exciting prizes for that. So be sure to join that. All right. See you, everyone.
Okay. Thanks very much. Bye.